In this video, we're going to look at electromotive force, potential difference, and the maximum power theorem. In the previous video, we looked at Kirchhoff's laws and resistors in series and resistors in parallel, deducing the formulas for resistors in series and resistors in parallel. Now, EMF is used when an electrical energy is being produced from other forms of energy. For example, in batteries, electrical energy is produced from chemical energy. In generators, electrical energy is produced from mechanical energy. The EMF of a source is the electrical energy produced per coulomb of charge passing through the source. EMF is equal to energy transferred over the charge. So E is equal to W over Q. The total work done per unit charge when charge flows around a complete circuit is the EMF. A battery of EMF 12 volts gives 12 joules of energy to each coulomb of charge passing through the battery. Right, so we do have that 12 volts passing through. So this is the energy that they have per coulomb passing through there, and then we're going to dissipate 8 joules, so depicted by minus 8, and then going to dissipate again 4 joules, and then back again to there, rejuvenated, come back again, lose the energy, rejuvenated, and so forth and so on until the battery has been depleted. PD is used when electrical energy is changed to other forms. So please remember that EMF, electrical energy, is converted from other forms. PD is when electrical energy is changed now to other forms in a component, e.g. a lamp. Potential difference is defined as the energy changed into heat and light per coulomb of charge passing through it, or the work done per unit charge in moving the charge between 2 points in a circuit. So PD is equal to energy transferred over the charge, so V is equal to W over Q. So EMF is equal to W over Q. A voltmeter placed across the terminals of a cell when it is not supplying a current measures the EMF of the cell. So EMF is the PD in an open circuit, so the PD across a battery in an open circuit. Internal resistance in terminal PD. Sources of EMF have internal resistance to current flow. In a battery or cell, this is due to the chemicals used in the battery. In a power supply, the internal resistance is due to the components inside. The internal resistance of a dry cell is about 1 ohm, and for an accumulator is about 0.01 ohms. When a cell is supplying current, its output PD is less than its EMF. Output PD is less than the EMF. This reduced voltage is due to energy dissipation in the battery due to its internal resistance. So like that, so we have the source, and then we've got this internal resistance due to the chemicals that are inside the battery. The combined resistance is that of the external circuit and the one that is in the internal in the battery. So it's going to be R plus R. So the total current through the cell is going to be equal to I is equal to EMF over the total resistance, which is R plus R, big R plus small r. So EMF will be equal to I, the current bracket, R in the external circuit plus R in the internal circuit. So IR plus R. So EMF will be equal to big V plus small v. Now big V is going to be the terminal PD. That will be the terminal PD, correct? And then small v is going to be the lost PD, that is lost to other forms. So IR is the terminal PD, which is equal to the PD across the terminals of the cell. And small letter IR is going to be equal to the PD across the internal resistance. And rearranging to get the terminal PD is equal to the EMF minus I small letter r. From energy considerations, since energy is conserved, EMF E is equal to energy supplied per coulomb from the chemical energy of the cell. V is equal to energy delivered per coulomb to external resistor R. Small v is equal to the energy lost or wasted per coulomb on the internal resistance R. Wasted energy is dissipated as heat. That's why you find the battery warms up when it is in use. This is because of these lost volts inside. The graph shows how the terminal PD varies with the current. If you have V is equal to E minus IR and you're plotting V against I, so which means your gradient is going to be equal to minus R, and then your y-intercept is going to be equal to E. So EMF E, right, is the terminal PD when there is no current flowing. That's when there is an open circuit. And then it starts to drop as you connect the circuit. Now there's a current inside, it starts to drop. Now the fact that it's got a negative gradient it is testified to by this, which is minus R. So minus R is our gradient. So when the current is 0, then V is equal to the EMF. So when the battery is in open circuit or no external circuit, the PD is equal to the EMF. Then when R is equal to 0, V is also equal to 0. This is when the battery is short-circuited in delivering the maximum possible current. So I maximum is equal to EMF over the small internal resistance of that, which is very dangerous. A battery is connected in series, that's an example, with a variable resistor and an ammeter. When the resistance of the resistor is 10 ohms, the current is 2 amps. When the resistance is 5 ohms, the current is 3.8 amps. Find the EMF and the internal resistance of the battery. So we're going to get the formula E is equal to I bracket R big R plus small letter r. Now we're given this current, which is 2 amps, and the big resistance 10 ohms from there. Then we want to find the internal resistance, so we just solve this equation. So we come up with E is equal to 20 plus 2R, and then we have again a set of readings given. So new current is 3.8 amps and new R is 5 ohms. Then we form a pair of simultaneous equations, and then you solve those. When you've done that, you find that you'd get R is equal to 0.56 ohms. Now, the last thing to talk about in this video is the maximum power theorem. Now, maximum power from this graph here, just jumping the gun, maximum power is delivered right there when the load resistance is equal to the internal resistance of the cell. That's where you've got maximum power delivered. So multiplying the equation by the cell current, remember we have E is equal to R IR plus IR. Now if you multiply by I both sides, you're going to get EI is equal to I squared R plus I squared small letter r. Now EI is the power supplied by the cell, I squared R is the power dissipated in the external circuit, and then I squared small letter r is power dissipated inside the battery. So the power delivered to R is I squared big R, which is equal to E squared R divided by bracket R plus R squared, since I is equal to E over R plus R. I hope you follow that. So from the graph, you've seen that the maximum power is delivered to the load when the load resistance is equal to the internal resistance of the source. The load is then said to be matched to the source. For example, an amplifier delivers maximum power to a loudspeaker when the output resistance of the amplifier matches the input resistance of the loudspeaker. Right, I'm going to end the video here. And then in the last video on DC, we'll be talking about the potential divider and the potentiometer. Signing out.